let's talk about the units of measurement. So in chemistry, basically in chemistry and science in general, it's all based on measuring. So we talked about how we study the chemical and physical properties of matter. We study this by measuring it. And the changes that they go through, we study this by measuring. And the energy that they give you, we study this by measuring. So we have a lot of measurements, and that's what we're going to talk about. I'm going to introduce a few measurements that we use depending on what you have. And so I'll tell you right now that in science, we use the metric system because the metric system is much better than the imperial system. As much as we use the imperial system, it's just not consistent when it comes to science and scientific measurements. So we can use them in common language, but when it comes to science, we're gonna use the metric system. So this is the imperial system. Let me show you an example, right? Look at how, when it comes to length, weight, and volume, look at how all of these are. None of it is related to the other. But when you look at the metric system, look at this, right? Each one is bigger than 10 times bigger than the other. They all work together, and you can use the same scheme when it comes to length, volume, and mass. You can use the same scheme where you have milli, micro, nano, pico, and all that stuff. So it's really, really cool. And again, for this class, we're going to need to know when it comes to, so the first unit, the central unit can be either liters, meters, or grams. Right? So that's volume, distance, and mass. And then I want you to know kiloliters, kilometers, kilograms, which is 1,000 times. And then I want you to know milliliters, millimeters, and milligrams, which is 1,000 times grams, right? And then when you divide that by 1,000, you get to micro. So I want you to know these four, and I want you to know these because these are the ones that we use a lot. We use these a lot. All right, so let's look at individual symbols, and then let's look at what we use in science when it comes to those. So let's start with weight, mass, and weight. So we have this international standard called SI. So whenever I say SI unit, it's the international standard. So these are scientists who sat down and they were like, okay, we're going to use this as a standard. So the SI unit for mass is kilogram. It's a kilogram. And remember that, we need to remember how the kilogram relates to other ones. And how does it relate to the other one? We know that 1 kilogram is how many grams? 1 kilogram is 1,000 grams, right? 1 kilogram is 1,000 grams. And then 1 gram is 1,000 milligrams. And then 1 milligram is 1,000 micrograms. Right, so those are the four symbols that I want you to know and how they relate to each other: kilograms, grams, milligrams, and micrograms. All right, those are the ones that I will need you to remember and know how to use. All right, so that's the mass. Now, again, we don't use the pounds. The pounds are just no. It's very confusing when it comes to pounds. But before I go to the next one, what's the difference between mass and weight? Because these are very different. So the mass is going to measure the resistance of an object to a change of its state of motion. So the mass is really it has nothing to do with gravity, right? So it's pretty much the force necessary to give an object a certain acceleration. But the weight is the force exerted by gravity. So the difference, if somebody asks you, what's the difference between mass and weight, what are you going to tell them? Gravity. That's the difference. Gravity is the difference. Weight takes into account gravity. So weight is force that gravity exerts on an object. So weight is going to be equal to the gravity times the mass. That is why on Earth, the gravity is 1. That's why you take c times mass is equal to, the weight and mass is the same on Earth, but it's not the same on the moon, for example. On the moon, a 1 kilogram bar will weigh 0.1 kilogram on the moon, right? So the weight will be different. But guess what? The mass is the same. So this one that weighs 0.1 kilogram on the moon, it will still have a mass of 1 kilogram, but the weight is going to be different. So that's the difference between the weight and the mass. And make sure that you can tell the difference, because it's a big difference that has a few implications that we're going to talk about. All right, what about length? The SI unit for length is meter. We're not going to use yard, we're going to use meter, right? And remember that we use meters. 1 kilometer is equal to 1,000 meters. 1 meter is equal to 1,000 millimeters, and then 1 millimeter is equal to 1,000 micrometers, and we're going to use all of them. So make sure that you know how they relate. What about volume? The volume of something, right? The volume is kind of interesting because look at this. If you have a nice cube, the volume of a cube will be multiplying the sides of the cube, right? But why does that matter? It matters because the SI unit for volume is cubic meters. Cubic meters is the SI unit, right? But even though that's the SI unit, we use liters a lot. So 1 liter is equal to 1 cubic decimeters, right? But in chemistry, we love liters, and we use liters because, again, it fits into that system where 1 liter is equal to 1,000 milliliters, 1 milliliter is equal to 1,000 microliters, and 1 kiloliter is equal to 1,000 liters, right? That's volume. Concentration is a bit different, but concentration is, well, give me a second, guys. So concentration is used a lot in chemistry, and it's the amount of substance in a defined space volume, right? It's the amount of substance you have in a certain volume. So think about it this way, right? If you have a flask and you add salt, right? In one you add just a little bit. In another one you add a little bit more. And in another one you add too much. So that's the concentration. If you have the same amount of volume, the same amount of water, and then you add different amount of salt, they have different concentration. So concentration is the amount of substance in a certain volume, right? We use concentration a lot, and we're going to have a chapter where we talk about concentration. Another thing that we talk about a lot is temperature. Temperature is pretty important because temperature is how we measure the change in energy, right? We're familiar with temperature. We always talk about temperature when it comes to weather and all that stuff, but we can measure, and we do measure temperature in the lab, and we use thermometers, right? We have different types of thermometers, though, depending on what we're trying to measure. And I'm gonna want you to know how to go from one to another, but it's pretty easy. The main one that we use is this one, right? The Celsius degrees. The Celsius is really cool because 0 degrees Celsius. Hold on just a second. So 0 degrees Celsius is the temperature at which water freezes. So water freezes at 0 degrees and it boils at 100 degrees Celsius. So that's the scale, 0 to 100, right? Water freezes at 0 degrees, boils at 100 degrees. That's the Celsius scale. So Celsius is based on water. All right, what about the other ones? So you have Kelvin and then you have Fahrenheit. Now you know that Fahrenheit is based on weather, right? Remember that, if you know that if you have 0 Fahrenheit, it's going to be really cold. If you have 100 Fahrenheit, it's going to be really hot, And Kelvin is used in something else that I won't get into. But how do you convert from one to another? Here's how easy it is. This is the formula. Kelvin is 0 degrees plus 273, and you can disregard the points 15. So we just say Kelvin is 0 degrees plus 273. So how do we use that? Well, if I ask you, like, how many Kelvin degrees are in 10 degrees Celsius? Well, all you gotta do is just see if you can see what I'm saying. So if you have 10 degrees Celsius, it's going to be 10 degrees Celsius plus 273, and then it's going to be 283 Kelvin. That's how easy it is. You just add 273 on your calculator. Now, Fahrenheit is a bit different, but it's still okay. If I give you degrees Celsius, all you gotta do is multiply by 9/5 plus 32 to get Fahrenheit, right? So if I tell you 10 degrees Celsius, Fahrenheit is going to be equal to 9 times 10/5 and all of this plus 32, right? So if I look at the calculator, 90/5, that's 18. 18 plus 32, that's 50. 50 degrees Celsius, right? So no, not 50 degrees Fahrenheit. So 50 degrees Fahrenheit. So yeah, 10 degrees Celsius will give you 50 degrees Fahrenheit, and then 10 degrees Celsius will give you 280 degrees Kelvin. So make sure that you know how to go from one to another. Another calculation that we use a lot is density. All right, we use density a lot to go from one thing to another. And density relates what? It relates mass and volume, right? So the density, all it is the ratio of mass to volume. That's it. And I love to give students this nice little formula that you should never forget. D is equal to M over V. That's it. D is equal to M over V. Just remember that. So as you would imagine, things that are heavy, like metals and rocks and things like that, they will have a higher density, and things that are light will have a very low density because it's the mass over volume. It's the mass over volume, right? So it's the mass that something occupies per volume. All right. So I can give you a question, but before we do that, again, these are the formulas, right? Density is equal to mass over volume, or D equals M over V, and the SI unit for density is kilogram per cubic meter or grams per milliliter. All right. So let's look at an example. An example is telling you a piece of a platinum. Let me see if you can make sure that you can see this. Yeah, so a piece of platinum metal with a density of this has a volume of this. What is the mass? Okay, this is actually a good one. So instead of asking you the density, they gave you the density and they're asking for the mass. All right, so they gave you, so I always, for every problem that you always have to write down what they gave you. So they gave you the density is equal to 21.5 grams per centimeter, cubic centimeter. And then they gave you the volume is equal to 4.49 cubic centimeter. And then they're asking for the mass. All right. So this is what we have. What's the mass? Well, what formula do we use? So after you lay out what you have, usually the second step is what formula do we use? Well, the formula says that the density is equal to mass over volume. Well, they are not asking for density. They gave you density. They want the mass. So what do? We solve for the mass. So we do cross multiplication, and the mass is going to be equal to density times volume, right? And all you gotta do is just now substitute. So mass is equal to, density is 21.5 grams per cubic centimeter times 4. Oh, I can't write here. Times 4.49 cubic centimeter. There you go. And then you just multiply on your calculator and you should get 96.5. So 96.5 grams, because the cubic centimeters are going to cancel out. All right, so that's how you work with density, and you should know this formula. Density equals mass over volume, and you should know how to move it around so that you can find anything that you want. All right. All right, I think that's enough about density. Now we're going to talk about significant figures. And you must have heard of these because these are very common in chemistry and in other classes as well. But significant figures is a measure of uncertainty. Why? Because you can't be certain of any number that you measure. So down there on this figure, you see how I have an example of a ruler, right? So if you measure a ruler like this, you can only be certain depending on what numbers you have on a ruler. So if you have between 5 and 6, and then you get something like this, how certain are you going to be? You can say 5.4, but you can't be like 5.48 or like 5.479. You can't be sure of that. You will be uncertain. So the uncertainty in the last number will assume to be plus or -1, right? So this is where we come up with what we call significant figures, right? So these are the numbers in which certain digits and the first uncertain digit are recorded. So we only record one uncertain digit. You know what I mean? So for example, here you can say 5.48 because we're not sure. So if you're unsure, you can only record one uncertain digit. All right. So significant figure are all the digits in a measurement with certainty plus one uncertain digit. But when it comes to chemistry, you need to know the significant figure rules, right? So the main place that you're going to meet significant figure is when you will have to measure how many significant figures, right? So I'll give you something, a number, and ask you like, how many significant figures are in this? And you're gonna need to find out using what? Using these rules right here. These 5 rules are what you're going to use. What are the rules? First of all, if I give you a number, any digit that's not 0 will be significant. So here you have 4 significant figures because it's 1, 2, 3, 4. There's no 0. Now, so that's the first rule. The second rule is going to deal with zeros. Zeros that are between digits, right? Zeros that are between non-zero digits will always be significant. So this is 3 significant figures. So that's okay. If you don't have any 0, everything is significant. If you have a 0 in between, everything is significant. It's only when you have zeros at the end when you start to have a problem. But it's not a problem as long as you follow the rules. So the first rule is saying that the zeros to the left, if they are at the end, they are not in between. The zeros to the left are not significant. So this is one significant figure. So these zeros to the left are not significant. Very important. All right. How about this? If you have zeros after the decimal point, they will be significant. Right? Zeros after the decimal point, they will be significant. All right. So, and this one is kind of like the above rules too. If you look at this one, the zeros on the left, not significant, but the zeros after are significant. So that's why you have here 3 significant figures. All right. So make sure that you know these rules, but let's practice. So how many significant figures are here? So what about the first one? What do you think? 3, right? Because there is no 0. 3 as well. This one, how many? 4, right? Because the zeros are in between. What about this one? This one, you have a 0 at the end, but it's after the decimal point. So 2 significant figures because that 0 counts. What about this one? Well, the zeros on the left don't count. So this is 3 significant figure. Same as this. What about here? How many significant figures? 2, because the zeros don't count. How about here? How many significant figures? The 0 at the end counts, right? The zeros after the decimal count. So this is 3. And this is 3 as well. How many here? Oh, this one is new. This one is interesting, actually. So the zeros are at the end, but not after the decimal count. The decimal point, they don't count. So this one is going to be 2, right? This one is 3, and then this one is 3. All right. That's significant figures. But another important point when it comes to significant figures is not just measuring the number of significant figures, but calculating, right? So there are rules that we follow when it comes to adding and subtracting. So if you add, so look at this. We're adding these two numbers, but they have a different number of significant figures. What do you use in your answer, right? This one has how many significant figures? 5. This one has 2. What do we use in your answer? Well, here's the rule when it comes to addition and subtraction. And I'm going to emphasize it because it's different compared to the multiplication and division. So the rule says that the answer is going to have the significant figure of the smallest one, but you have to look at after the decimal point. So you're going to count the number of significant figures after the decimal point and then use the one that has the smallest number. So that means that look at, between these two, the one that has the lowest is this one. So this one has 1 after the decimal point, and then this one has 3 after the decimal point. So that means that your answer is going to have one number after the decimal point. Same here. So in subtraction, you look after the decimal point. So this one has 2 digits after the decimal point. This one has 4 digits after the decimal point. So our answer is going to have 2 digits after the decimal point. That's the rule when it comes to addition or subtraction. What about multiplication and division? It's the same idea, but instead of looking after the decimal point, this one we're going to look at the whole number, right? So this has 3 significant figures. This has 5 significant figures. So you say, oh, even though my calculator says this, the answer is going to have the number of significant figures of the smallest one. So this one has 3 significant figures. So your answer has to have 3 significant figures. Does that make sense? Yeah? All right. So those are the calculations when it comes to significant figures. All right. So now I want to switch gears a little bit, and I'm going to talk about scientific notations. And you might have heard of these, but this is the idea behind them. The idea behind them is like, okay, we know how to measure all of these, and we just talked about how to measure these things, but let's say you're measuring the distance between here and the moon, right, in meters. It's going to be a long number, and you're going to have to write it down like a mile long. So instead of doing that, we've come up a way to shorten this, and this is called the scientific notation. So this is used for really, really, really small numbers or really, really large numbers. So that's where this idea of the scientific notation come from. And we're going to look at a few of these, all right? And the rule that we use. So again, this is an example of how this is really long. So this is called the Avogadro's number. Look at how big it is. So instead of writing it down this way, or the mass of a single atom of carbon, it's really, really small. Instead of writing this way, why don't we just write it down in a shortened version? So we write it this way, and this is called the scientific notation. Right? Now, right off the bat, I want you to realize something. Look at how the one that was really, really big has a positive number here, and the one that was really, really small has a negative number here, right? But we turn into this number to certain number times 10 to the other number. So we're going to see how to convert these and back. All right. So if you have a number that's above 1, so we're going to divide this into two camps. All right. If you have a number that's above 1, right, you're going to move the decimal to the left until you have one number left. Okay? Move the decimal to the left until you have one number. Right? So we're going to move this one, 1, 2, until you have pi point this, right? So we move this, and then you're going to say 10 to the number of times you moved the decimal. Right? So here we moved from 1, 2, so it's going to be 10 to the second. So you move to the left until you have one number, and then when you write it down, you say the number you have times 10 to the number of times you moved. And it's similar when you have something that's less than 0. When it's less than 0, you move the decimal to the right. So here we're moving it until you get to one number. So 1, 2, 3, 4, 5, 6. So we moved it 6 until we get to 7.72. And then when you write it down, you're like 7.72 times 10 to the negative 6. And this is negative because, again, it's lower than 0, but 6 is the number of times that we moved. It's really, really important. So let's look at an example. And this should be a chance for you to practice. So let's turn this into scientific notation, right? So this is going to be 2.4 times 10 to what? How do we get to 2.4? We moved 1, 2, 3. So it's 2.4 times 10 to the negative 3. How about this one? 1, 2. So it's 1.80 times 10 to the negative 2 because we moved 2. And look at this one. These ones are bigger than 0, so not lower than 0. So that means that we go to the left until we have one number. So it's 2.24 times what? Times 10 to the, how many times did we move? We moved 2 times. I don't know why it doesn't want to put it that there. 2.24 times 10 to the second because we moved only twice, and it's 2, not -2, because this number is above 0. How about this one? Right, I want you to pause and see if you can figure it out. But again, since this is above 0, we're going to move the decimal from the end all the way until we have one number. So we're going to get 6.673, right? And then times 10 to the negative what? And I mean times 10 to the what? 10 to the number that we moved. So we moved 1, 2, 3, 4, 5. So 6.673 times 10 to the 5th. All right. So some of them might kind of be tricky, like this one, but that's okay. It's already you already have a decimal point here, but that's okay. You just have to move it until you get to 1. So this is 7.2420 times 10 to the what? We moved it 1, so it's 10 to the 1st. Okay. How about this one? This one is below 0, so we move it this way. So it's 8.3 times 10 to the what? We moved it once, so it's -1. All right. So I'm going to leave you with these other ones for you to practice, but you should know how to convert into scientific notations and back, right? So for example, if I tell you, if I say, okay, 2.7 times 10 to the -3, and I tell you to convert it into your normal notation, -3, you will know that -3 means that it's below 0, right? Meaning that it's going to go that way. And 3 means that's the number of times that you jump. You're going to go 3 times, 1, 2, 3. So you know that you're going to go 0, 0, 0. So 0.0027. That's what is going to go to. So let me just write it down better. So 2.7 times 10 to the -3 is equal to 0.0027. So you should know how to go from here to here and back. So to give you an example of the other one, if I have 2.87 times 10 to the 3rd, right? If I say 3 instead of -3, that means that we're going that way, right? It's bigger than 0. So how much bigger? You're going to move 3, right? So if you move 3 is 2.87. If you move 3, if you move 1, it's going to be 8. If you move the second, it's going to be 7. You don't have anything else, so that means that it's going to be 0 here. 2870, right? So 2.87 times 10 to the 3rd is equal to 2870. So you should know how to go back and forth here, all right? Okay, so a few other things that you need to know. When you're adding or subtracting, you're going to need to convert what you're subtracting into the same unit. So if I ask you to add this to these ones, you need to convert. So that's what we did here. We converted one of them into 10 to the 4th so that we can add them up. You can't add them up if they have a different exponent, all right? Now, when it comes to division and multiplication, we have a rule, and you might have seen this in algebra. We have a rule that's really important, and it says that, look, I'm gonna write it down here. Let me see if I have space. So for multiplication, 10 to the x times 10 to the y is equal to 10 to the x plus y. All right. It's very important to remember. So that means that if I have something like 4 times 10 to the negative 5 times 7 times 10 to the third, I'm going to isolate 4 and 7, put them here, right? And then 10 to the negative 5 times 10 to the third is going to be equal to 10 to the negative 5 plus 3. So this is this rule right here. That's the rule of multiplication when it comes to scientific notation. Right? What about division? Is the opposite. Right? So 10 to the x over 10 to the y is equal to 10 to the x minus y. You gotta remember that. All right? But after that, you'll be able to do all the calculations that you want, and that should be enough about scientific notation. But I will give you a worksheet where you will have a chance to practice more and more. All right, so let's talk about accuracy versus precision. Right? So this is different terms that we use in chemistry. All right, so accuracy versus precision, what's the difference? Well, accuracy is how close a measurement is to the true value, right? And precision is how close a set of measurements are to each other, right? So when something is accurate, we're comparing it to the true value. But when something is precise, we're comparing it to the measurements that we're making, if that makes sense. So this chart down here illustrates it really well. Right? If something is accurate, so think about the target in the middle as our target. That's where we want to hit. If we're accurate, we're hitting it. And then if we're precise, we're hitting the same spot multiple times. That's accuracy and precision. But look at this. We might be precise but not accurate. If we're precise, we're measuring something over and over again and we're getting the same result. But we're not accurate because we're not hitting the right spot. So you can be precise and not accurate. And if we're all over the place, we're not accurate and not precise. All right? And this is particularly important when it comes to measurements of, we talked about the measurements, the distances, the concentration, the temperature, and all that stuff. And what do we use to measure this? A lot of sophisticated instruments. So these instruments, we always check for their accuracy, but also for their precision. So an instrument, to be able to be efficient, it needs to be accurate and precise. So you can't just have one, you gotta have both of them. All right, and I think that's enough about accuracy and precision. And let's switch gears and talk about unit conversion. Now we gotta know how to convert units from one to another. So we were talking about, I gave you different units and different units of measurements, but it becomes a problem when you go from one movement to another. So this is an example of how the units that we've been looking at relate to each other, right? So you might think like, oh yeah, I can just convert from liters to volt to milliliters, whatever. But what if I give you 1 gallon, right? And you have to go from 1 gallon to liters. Well, there's a conversion factor, but how are you going to do that? How are you going to calculate that, right? So if I give you 1 liter, where is it? Okay, so 1 gallon is equal to 3.78 liters, right? Good. And then I ask you, like, what about 12 gallons? You're going to multiply, right? So this is unit conversion. So you have different conversions. For example, miles to feet to inches, miles to kilometers and things like that. So you have a lot of different types of conversions. But if I give you a conversion factor, how are you going to give me a conversion, right? So this is where we're gonna need something that we call dimensional analysis. But don't be intimidated. I'm going to show you what this is using a few things. So I'm going to start with level 1. So this is not level 3. This is level 1. And level 1 is converting units, right, within the same system. So let's say I give you convert 2 kilometers to meters, right? Now I'm going to give you steps that you're going to use every time when it comes to conversion, right? Because you really need to know how to follow these steps, because if you don't have a system, it can be confusing. So the first step is you start with, so if I give you this, convert 2 kilometers to meters, the first step is find the formula. Is there a formula for conversion? Yes, we have it. That's the first step. Find the formula. So the first step is find the correct formula, all right? And we found the correct formula, conversion formula, right? So that's the conversion formula that I gave you. 1 kilometer is equal to 1,000 meters. That's a conversion formula. Step 2 is start by writing down what you've been given. So what's given here is 2 kilometers. Start by writing down what you've been given. What's the next step? You're going to multiply what you've been given by a conversion fraction. This is where a lot of students get it wrong. You're going to multiply this by conversion fraction, and the conversion fraction is going to be coming from the conversion formula. All right? So from the formula, you're going to figure out which one goes to the bottom, which one goes to the top. And what do we use? We always put what you have here. The unit you have here is what you put to the bottom. So the 1 kilometer is going to go to the bottom. The 1,000 meters is going to go to the top. Very important. And why do we do that? This is so that the kilometers can cancel out. So this one is going to be equal to 2,000 meters. Now, guys, you might look at this and be like, oh, that's easy. That's easy. I'm not going to be using the fraction method. I'm just going to multiply. But that's where a lot of students get caught up, because you're not always multiplying, right? So this takes me to level 2. What if, instead of asking you the straightforward way where you have to multiply, I ask you where it won't be as obvious whether you multiply or divide. So I say convert 2 meters to kilometers. So again, find the formula you have it. I gave it to you. 1 kilometer is 1,000 meters. And then you start with what's been given. So you always start with what's been given, which is 12 meters here. And then you multiply by the conversion fraction. The conversion fraction, again, is really important. You get it from the conversion formula, and you make sure that what goes at the bottom here is what you have here. So here you have meters, meaning that at the bottom you get meters. So 1,000 meters here, and up here you have 1 kilometers. All right. So it's going to be 12 times 1 over 1,000. Which is 0.012. kilometers. All right. So you see that you have to use the same. You have to use the same steps, but it's not always obvious, like, oh, I have to multiply or I have to divide. So that's why you have to use the same steps. And again, the steps I gave you, you find the correct formula, start with what you've been given, you multiply by the conversion fraction, and the conversion fraction comes from the formula, and you make sure that the unit given are at the bottom, right? So the units given, the meters, for example, here are at the bottom. The meters are at the bottom, right? And then the units needed are at the top, and then you cancel the units and then you calculate. So here we canceled out the meters and then we calculate. All right? Good, right? All right, so that should be enough, but let's go. So that's level 2. Level 2, we have to divide. What about level 3? Level 3 is when I give you, when you have to do two different conversions, right? So let's say I give you convert 2 inches to millimeters, but if you look at the formula I give you, I don't give you a formula from inches to millimeters. I give you the formula from inches to centimeters, and then from centimeters to millimeters. What does that give you? It gives you, it tells you that we have to go from inches to centimeters, and then from centimeters to millimeters, right? So you gotta do two conversions, but it's okay. We use the same idea, right? So you start with what you've been given, which is 12 inches. You multiply by the conversion fraction. What goes to the bottom here? It's inches, right? And the formula for this is the formula for this. Say 1 inch equals to 2.54 centimeters. So the inches go to the bottom. 1 inch go to the bottom because you have inches here, and then 2.54 centimeters go here. All right. So far so good. You just went from inches to centimeters, but we're not done. We have to go to millimeters. What do? You multiply by another fraction. You multiply by another fraction. And you're going to convert from centimeters to millimeters. So it's the same idea. We have the formula here, right? We have the formula that you gotta use here. And all you have to do is figure out what goes to the bottom. What goes to the bottom here is the centimeters, because you have centimeters here. So 1 cm here, and then on the top you have 100 millimeters. All right, so that is how you do it when you have to do two conversions. And all you gotta do is just do it on your calculator, right? Make sure that you write it down the right way on your calculator. So the best way to do it is to do the top portion by itself, and then you do the bottom portion by itself, and then you can divide them at the end. But for this one, the bottom portion, we all have ones, so we're not going to put anything. So 3048, that's the answer. $3048 millimeters. That's the answer. So that's what happens when you have to do two conversions. Nothing fancy. All right, let's go maybe one more level, right? Another level is if I ask you the fraction. By the way, even though, one thing that I'm trying to show you is that all of these levels are still using the same steps. All right, and I don't want you to be intimidated. I just want you to recognize it. I know that you gotta use the same thing. So level 4 is when I give you something that's a fraction. What does that mean? 70 kilometers per hour. It's kilometers per hour. And then I ask you to convert it to meters per second. So this is a fraction. All right? And a fraction, you treat it the same way, but you have to treat these two differently. So look, 70 kilometers per hour, you write it down 70 kilometers over 1 hour. And you know how to convert this into meters per second. How do you do that? You're going to convert the top by itself and the bottom by itself. So 70 kilometers, let's convert it into meters. Well, we do it the same way. You start with what you've been given, 70 kilometers, multiply by the fraction. So the fraction, the kilometer goes at the bottom, the 1,000 meters go at the top. And this is going to be, before we say what it's equal to, let's also convert the hours. So the hours need to go to seconds. And the hours, it's not actually 360, it's 3,600 seconds. So 1 hour is 3,600 seconds, right? So the kilometers cancel out. So this is going to be equal to 7,000 meters over 3,600 second. All right. And it's going to be 1.94 meters per second. So this is how you convert kilometers per hour to meters per second. It's still the same idea, but you just have to divide the two and convert them separately. So these are the 4 levels of conversion, and you should know how to do each one of them. If you're given a conversion table like this, you won't have to memorize these, but I want to, when I give you a conversion table, to convert anything to anything else by using the steps that we just went through. All right. And I think that should be enough. That should be enough for this chapter. And make sure that, again, you replay it. You try to make sure that you understand it. You're free to always ask me questions. And also, after understanding, make sure that you use the material that I gave you to practice it. Because even if you understand it, if you don't practice it, it won't stick. So I really want you guys to understand it, because this first chapter lays the foundation for what's coming next. All right, I'll see you next time. Bye-bye.